It is my pleasure to introduce Dr. Szymon Cygan from the Mathematical Institute at the University of Wrocław. He's an assistant professor there. He's a recipient of the International Prize for the best dissertation in mathematical sciences. He got the distinction there. So that was in 2023. So it means he's only young, but he's the youngest speaker of this conference. He got the PhD under the guidance of Professor Grzegorz Karp. The PhD was about patterns in mathematical biology, concerned partial differential equations, practical diffusion equations, and basically instability of stationary states. So he's a mathematical biologist or biological and at the same time biological mathematician. So the idea is that he investigates the application of biology to mathematics and mathematics to biology.
Exactly.
Yes. So the topic is yours.
Okay, so thank you very much for the very nice introduction. I'm very happy to be here to have the possibility to give a talk about this side. So thank you very much for the organizing, for inviting me here. It is a great pleasure. So today I would like to talk about the Turing patterns in mathematical biology. Because there are plenty of biological applications where we can observe different diversified patterns, namely some regular structures or repeated sequences, which occurs in very diversified areas. And today I would like to propose a very simple mathematical way. How can we describe the process? How do such a pattern happen? And the idea is the following. So first, let me start with the motivation. And the motivation is like this one. Take a look at this fish. So if you examine this fish very, very closely, you can see a very regular pattern on its skin. Here we can see stripes, yellow and blue, yellow and green stripes, which starts from the head and goes up to the tail. This is an example of an animal fish. And one can ask, why does such a fish possess such a nice pattern? Because does the fish know how to produce such a pattern? Or maybe this is a result of some reactions of some processes that occurs inside of the fish skin, and the patterns is just the result of this process. And in this talk, I will try to explain this process as simple as possible, using differential equations, in particular, reaction diffusion systems. So it occurs that we can observe such a phenomenon in very different methods. For example, if we take a look at this, at this fish, this is booby fish, the first one, the second one, and the third one are the booby fish, and the last one is the Japanese fish. And if you look really closely, you can see that on each of these fishes, you can see a pattern. And this pattern now can be very, very diversified. It can be spots, it can be stripes, it can be something different, like here, black paths and the red paths distributed across the whole. Like on the first one, the second one, also something irregular which appears here. And this phenomenon was studied very, very intensively by plenty of scientists, mathematicians, biologists, and so on. Everyone would like to know why such a phenomenon occurs. And there are some biological explanations that production of this pattern, so emergence of this pattern, can result from two very simple phenomena, which I will explain in a moment. But before this, let's meet our new friend. Let's call it Paul. This will be our new pet friend Paul. And during the whole talk, I would like to focus on this case. Why? Because if you look very closely at him, you can see patterns. Like here, there are spots on the whole cat one. On his back, on his belly, on his paws, all of them. But the very important thing we can see here is that if we take a look at the tail, then at the tail something happens. what happens? The patterns on the tail differs. It is different than on the back, because here there are spots, and here we can see the stripes. So why it happens that on the body the pattern is different on the tail? Was it supposed to be like that? Or maybe this is just an accident. So basically, we try to analyze this phenomenon, provided that we will use only two simple phenomena from biology. So to sum up the first part, patterns are frequently observed in a very different ways. So they can be observed in biology, in medicine, in ecology, in the growth of the plants, in the distribution of the trees, in the flow of the water, formation of dunes, almost everywhere. So they are like thousands or even millions of different areas where you can observe those patterns. They play very different roles. They can be used in mating. They can be used in verifying your opponents when you're an animal. They can be used to hide as a part of the count. So there are tons of different applications of this pattern. But the most important thing is the last one. That if you take a very, very close look at this pattern, they are almost in order to do the pattern, we need to have at least two different colors. So we need to have at least two different pigments. So here they are called pigments, so a colorful substance, which somehow influence the shape of the pattern. And in order for the pattern to exist, we need to have at least two different dyes, two different pigments. So now let's switch to mathematics. We are here on a mathematical conference, so we will try to explain the process of forming patterns using mathematics. And the idea is the following. We have two very simple laws which follows from biology: the reaction and the diffusion. And both of them can be observed in biology almost every day. The first one says the following: that if we have a substance which is produced by an organism or by some plant or by any individual that lives on our planet, the production varies in time. It is not constant. So sometimes it can be bigger, sometimes it can be smaller, sometimes it can be even negative if the amount of some substance is decreasing. But the reaction states that the rate of production of some substance depends on the total amount of the substance, or also depends on the mutual interaction between different substances. So, for example, if you take a look at our car, and you like to analyze the components. So the pattern results from the production of the time, the production of the speed. So reaction states that the production of this party depends on the total amount and total distribution of this dye around the whole body of this organism. And the second very important element, or second very important phenomenon, is the diffusion, which states, just as the usual diffusion, that if we have some substance concentrated at some point of the space, then as the time passes, the substance will spread along the whole area, so that the substance will diffuse across the whole domain where it's located. So now we would like to discuss both of these elements, so reaction and diffusion, how to model them using differential equations, and then we will talk about how we can obtain patterns just by using those two phenomena. So the first one is reaction. Reaction can be modeled as the simplest case using ordinary differential equations. And look, what do we have here? Let's assume that we have n different substances, which densities are denoted by U1 to U. So each of these densities is denoted by some variable U1 to Un, which depends on time. And then we have the following system of ODEs, the following system of ordinary differential equations. We say that, okay, if we want to know what's the rate of change of the function U1, so how fast do we produce, or how fast the amount of the substance you want to produce, we need to know what is the total amount of the all substances you want to up to your object. And then compute the value of the function f, which is some nominality. It gives us other information. What's the influence of all of the substances you want to add to the production of the element you want. And the same equation you write for all lines, for all pigments. You want you to up to your value. And then we obtain the simplest model of the reaction. And now what can we say? Well, basically, this is the system of quantities of ordinary differential equations. So using the basic knowledge from the course of the ordinary differential equations, we can write it in the matrix form, like here, where here u is a vector, u1 up to un. Function f is now the vector value function from f1 to fn. And then our system written in this way now becomes written in this way. Like here we have the time derivative vector from u1 to un, and here we have a vector of functions f1 or up to fn calculated at points u1 up to un.
So there's a stupid question. So why is this called direction equations? This is a general form of the orthogonal differential.
Yeah, and from biological point of view, this is exactly reaction. This is how they call it. Because they introduce the same reaction to explain that something is reactive. And the simplest model of reaction is just the usual of it. Nothing more sophisticated.
Okay.
Yeah, sure.
Can there be a memory effect?
Yes,
Depends on the previous.
Yeah, this can be.
Because you wrote.
Yeah, of course, this is just the simplest case. You all know. If you want to have a memory,
Possible.
of course, for example, you can have fractional time derivative, or you can have equations with the time delay or something else. So basically, there are plenty of possibilities how to introduce delay. But this is just the simplest case. Okay. So basically, from the course of the differential equation, from the theory of the ordinary differential equations, we know that there exists local time solution. But we can the more important thing concerning part information and the reaction is the stability case. So for example, if we have this system of ODEs, then we need to introduce the concept of asymptotic stability because we will use it during the whole talk. What does it mean? If we have such a reaction with the initial condition of u0, and then we know how to behave our function u, which differential equation does it satisfy, then the definition of the asymptotic stability is following. Well, what happens? We would like to know what happens if we take the initial condition and we introduce small perturbation. So basically, the stability means that if we take our initial condition and introduce the small perturbation, then the solution of our differential equation will converge to our previous solution as time passes to infinity. So basically, it means that the small perturbation of the initial condition will not grow in time. So basically, that the perturbation will vanish as time passes to infinity. And now, okay. So now we will have the following concept. We take a constant solution, and during the talk, we will analyze the stability of the constant solution. So what is constant solution? Notice that if we take the vector u(r), which is n-dimensional vector, such that the function f at this vector is equal to 0, then this constant vector u(r) is automatically a solution to our equation. Why? Because if I substitute my function u(r) into this equation, this term will be equal to 0 by our assumption. And also the time derivative of a constant will not depend on time, this is 0. So basically u(r) will be our solution. And now we would like to study the stability of this constant solution. And how do we do that? Well, the idea is the following, that we will linearize the right-hand side of our equation using Taylor expansion around the constant solution u(r). And this is what we get. So we substitute that u is equal to our constant solution plus some perturbation time, compute the time derivative, On the left-hand side, U bar will vanish. And on the right-hand side, using Taylor expansion, we'll obtain the following expression. This is equal to 0 by our assumption. And then our solution, our solution for the function phi is the following. And now there is a criterion which states under which condition the solution to the system is stable. And it is the following. The solution to the system is stable only if asymptotically stable, if and only if the eigenvalues of this matrix F prime computed at the point of U1 have all eigenvalues with strictly negative values. This follows from the exact expression for our solution. And on the other hand, if F prime, so our realization matrix computed at the point U prime, has an eigenvalue with the positive real part, then the solution automatically takes us. And just to clarify the things I'm talking about, let us consider a very simple example, which is the product of integral. And here we have, okay, two-dimensional system of two oddities, where we have on the left-hand side the time derivative of u and of v. On the right-hand side, we have some nonlinearities. We describe some dynamics between the substances u and v. And notice what happens. The function r on the right-hand side is just the vector valued function from R2 to R2. On the first coordinate, this is this expression. On the second coordinate, this is this expression. Then we can compute the time derivative, derivative of the function f. So the derivative with respect to the first coordinate and to the second coordinate. This is the expression we get. Then we compute the steady states, which are here 0, 0, 1, 1. We compute the realization matrices at the first point, at the second point, and if we compute the eigenvalues, we'll obtain that here. We have one eigenvalue positive and one negative, where here we have two eigenvalues negative, which means that this one is nearly stable and this part is unstable. And now what happens? So we have introduced the first concept, called here reaction. And now we will switch to the second concept, which will be called the diffusion. So basically, the diffusion is the following. In biology, this is a phenomenon which describes the splitting of a substance along the domain. So imagine that we have something concentrated at a certain point of the space. Imagine that there is a substance concentrated at a certain point of the space, and as the time passes, the substance will spread along the whole domain. This is exactly what happens. Every red dot is spreading to some points of this container. And basically, diffusion should be a process which describes the homogenization of some substance along the domain. So this should be something that as the time passes, our substance will be uniformly distributed along the whole domain. And basically, diffusion can be described also using differential equations. And the equation for the diffusion is the following. So this is like the time derivative with respect to u is equal to the second derivative, or here in the general case, as the sum of second derivatives. And we also need to supplement this equation with some initial condition and with some other. So basically, this is a normal model for the heat. This is the normal model for the equation. And this model, this equation, can be expressed or can be derived very nice from the random walk-up. And it is the following, because it should describe the process of spreading some substance along the domain. And imagine the following. Imagine the set of integers, and imagine a very confused man at the middle of the slide. And he is doing the following. So he has completely no idea what he will do. He doesn't know where he wants to go. And that's why at every point, at every time, every second, he is taking steps, either to left, either to right, but he is doing it completely random. He has no idea where he wants to go. He has no plan. That's why he's like, okay, maybe one step right, second step right, one step left, and so on. So he's taking this random walk around the real life. And now imagine what happens. Imagine he would like to compute or divide the probability that the man that starts his walk here at the point of 0, what's the probability that this man, after n seconds, will be at the field X. And in order to compute that, we need to write some recurrence. So imagine how we can express the probability that after a certain time, our guy will be at the point 0 again. And basically it is the following. If the guy after n seconds will be back at the point 0, it means that 1 second before, he was either on the field number 1 and did the step left, or he was at the field number -1 and made a step to the right. So basically, it is exactly this recurrence. Probably that he is at the field X at the time T means that he went the 1 second before. He was on the left hand side and made a step to the right with probably 1/2. Or he was on the right hand side and he made a step to the left with this probability. And after that is the following. Okay. If we subtract from this equation this quantity, probability of being at the point X at the t-1 from the left hand side and from the right hand side, then this expression on the left hand side and this expression on the right hand side, they look very, very familiar. Because look, this is the difference of probabilities at the time t minus the probability at the time t-1. So this is something which looks exactly like the time derivative of t up to some constant. And on the right hand side, we have something that looks like exactly like the second derivative of t with respect to x. And this is exactly how we derive this equation. Here we have time derivative, and here we have sum of the second derivative with respect to x of our function. And now is the following. We also need to impose something more. We need to impose boundary conditions and the initial condition. Why? Because first of all, when we start our random walk, we need to know the exact location of our view. Because the random walk will look different if you start from the point 0, from the point -1, -2, or +3. So we need to know the distribution of all the guys along the integer line. And also is the following. Because here we assume that this line of those integer is infinite. So he can make as many steps to the left or as many steps to the right as he wants. However, in real world, this is not the case. Because if we think, for example, about any organism, like a fish or a cat or something, then the domain so the area of this organism, it is finite. Therefore, we need to somehow assume that also this random walk takes place on a finite domain. And now we need to impose, okay, what happens? For example, if we will consider this walk only on the interval from -5 to 5, then we need to also impose what happens when our guy hits this level -5 or hits this level 5. And basically, there are two most common outcomes, which are called boundary conditions, and the states either that if the guy hits the level of -5, it falls the hole. So we assume that there is a hole here, that if he comes to the field of -5, he cannot leave it. So he will stay here forever. Or we assume that there is a wall here, which means that he cannot pass through the wall. If he hits the wall, he will be reflected and he will go back to our domain again. And those two are exactly called zero boundary condition, which are called the delete, or no flux to the boundary, which you can think as the wall which is placed at the point -5 or at the point 5, which means that our guy cannot go through the boundary. And now something hard. So basically, the solution to the heat equation, the bounded domain, can have an exact solution. We can provide an explicit formula for the solution. But in order to provide this solution, we need to use something hard, which will be called the spectral theorem of Laplace. Because basically here, this operator here, this delta, it is Laplace, it is called Laplace, so the sum of the second derivative. And the spectral theorem, it states the following, that we can think, roughly speaking, about the Laplace as we can think about the Laplace as on a large matrix. So it behaves somehow as a large matrix. What does it mean? It means that we can, roughly speaking, we can diagonalize. So it means that there will exist an infinite sequence of an eigenfunction, which was the generalization of the eigenvectors, which has the following property, that if we compute the Laplace operator at the function ek, so at the eigenfunction, it is exactly the same as taking the eigenfunction and multiplying it by some eigenvalue lambda. So this is completely analogous to the diagonalization of the matrices. We want to express our operator in some matrix using the spectrum, so using the set of eigenvalues. And basically, there is a theorem, this theorem states that the set of an eigenvalue, the set of an eigenfunction, this is a basis of the space of L2, which means that our function, our solution, can be expressed as an infinite sequence of our eigenfunctions multiplied by some coefficients which depends on time. So this is a theorem. And using this property, it is extremely important because now we can compute an explicit form of our solution. Because look what happens.
Sorry, I understood it.
Yeah, sure.
Boundary condition, but the spectral theorem is used for Neumann, which is another person.
Sure. Yeah, sure.
Thanks for the original spectral theorem in this context, but the more powerful spectral theorem was definitely by Neumann.
Yes. Sure. So here, technical annotation, it should correspond to the boundary conditions.
No, it's written correctly.
Yeah.
But what?
Yeah, sure. Thanks. Okay. So now we take a look what happens. Basically, we have the following behavior. We have our heat equation. We have the expression of our function u as a series using the eigenfunction, multiplied by some elements, time-dependent elements. And we substitute our function u into the equation, into the heat equation. And what happens? The following thing happens. Time derivative comes into the sum, under the sum. And we obtain the equivalence of those two sums. And now, using the previous theorem, since the functions ek, they form an orthonormal set, it means that since this equality holds, then the equality holds for each k, which means that every coefficient ak, satisfy the following differential equation, that the time derivative of ak multiple is equal to ak multiplied by lambda k. And this quantity has a solution given by an explicit formula. So this is just an exponential function where the exponent is equal to lambda k multiplied by k. And now we can write an explicit formula for our solution. But we can tell a lot of things about the solution because we know the properties of the function of the eigenvalues lambda k, and we know that we have a lot of information about the eigenfunction. Because first of all, the eigenvalues here, they are strictly negative. So they are less than 0 and they diverge to minus infinity. And also, the first eigenfunction, it is constant. And look what happens now. If we take a look at our solution, it means that since all of the eigenvalues lambda k, except the first, they are negative. So it means that this quantity, as time goes to infinity, this will converge to zero really, really fast. So all of these terms under the sum, they will converge to zero, except of the first one, where lambda k is equal to zero. Because lambda 1 is equal to zero. So it means that as time goes to infinity, all of the terms here will vanish, except of the first one. So basically, it means that every solution of this equation with the Riemann boundary condition, it will converge to constant. So this is exactly what we wanted. So we obtain that if we have this equation, will preserve the most important property of the diffusion, that despite of the initial distribution, after a very, very, very long time, the substance will be distributed homogeneously along the whole domain. So this has the property of homogenization. And it means exactly as presented on this simulation, we have the initial condition on the red one, and then it stabilizes, and converges to the constant. So it will be, after a very long time, it will be. And now, let's move back the patterns. So we will connect those two phenomena, the reaction and the diffusion, and see how we can obtain patterns just by using reaction, just by using those two. And the first one is the following. Imagine first that we have only one single equation. So no system of reaction diffusion equations, but only one equation. Only one function rho, which depends on x and t, only one Laplace operator, and the function f, which comes here from R to R. So this is just the usual function. And notice that what happens. So we consider this system, and I would like to understand if it's possible to obtain patterns only in the case of a single autonomous equation. But it occurs that in the case of one equation, something strange happens. Because we have function f, which corresponds to some production of a substance along the whole domain. We have the Laplace operator, which makes the which forces me to make the homogenization. So she forces the substance to be distributed uniformly along the whole domain. And now we'll take a look what happens. Imagine that we have a constant solution. So we have a number, so that our function f at this evaluated at this point is equal to 0. So basically, this number is a stationary solution of our system, because time derivative of constant is 0, Laplace of a constant is 0, f of this constant is 0, the equation is satisfied. And now see what happens. I'd like again to linearize my equation around this constant steady state. And I apply the following equation for the linearization. And now I would like to study what can I say about the stability of the constant steady state. And basically I can say the following, that if I have this linearization, I can compute using the same technique as in the case of the heat equation. Yeah, sure, of course.
So how yes, I wanted to ask, so how do we restrict it from a case that right there it says function f in C1 is arbitrary, but then we use the Taylor expansion. So how we restrict it to a holomorphic f or
Yes, of course.
okay. The results that come next then are for holomorphic f?
No. Well, so of course it is arbitrary, but I didn't write it precisely. Of course, we wanted to be holomorphic or at least even expressed in the form of the Taylor series.
Okay, and is that needed for the next argument, or is it
basically no.
Okay, for exposition?
No, of course. Basically, we have the first term in the Taylor expression. We do not need to have the whole series. We just need to have the first term for the linearization.
Great.
Yeah, what's thinking about the remark, of course. Sure. So now is the following. We introduce the linearization. And using the same technique as before, so this eigenfunction we can write the explicit expression for the solution. But see what happens. Imagine that this solution U bar, it was stable. So what does it mean? If the solution U bar was stable in the system without the diffusion, so without the Laplace term, it implies that the time derivative, that the derivative of the function computed at the point u bar equals negative, because this is the condition for the asymptotic stability. So imagine that u bar is stable and this term is negative. But this means that if this term is negative, and all eigenvalues of the Laplace operator are also negative, because this is the statement of the theorem, it means that here this term in brackets, it is negative for every case. So it means as the time passes to infinity, every exponent will converge to zero, because every term here every term here is negative. So it means that in the case of a single autonomous equation, if we just one equation, fraction diffusion equation, every stable solution without the diffusion will be also stable with it. So we can basically there is a theorem that in this case of single autonomous equation, we can obtain no half. So every constant solution, the only solutions that are stable are constant. Every non-constant cannot be stable, and then they cannot be offset in by. So now we can ask, okay, how is it possible that we somehow observe points? But the first analysis stated that it is impossible. And here comes the Turing instability. And the Turing instability is a genius idea, which was introduced by Alan Turing. This is exactly the guy from the Turing machine and from the Turing. In his seminal paper from the year of 1952. Because in this work, he studied the process of morphogenesis. What is that? This is the state of the development, this is the process of the development of the human body during the first weeks of life. So, or even the first months. And he wanted to understand how is it possible that from the one single cell, we can obtain the whole human. How is it possible that there are some symmetric reactions? That from the single cell, then we obtain hands, we obtain head, we obtain legs, and so on. How does it occur? And he proposed the following explanation: that he made the observation that I made at the beginning of the presentation, that in order to obtain patterns, I need at least two different types, two different substances. I cannot obtain patterns if I have only one substance, because then the reaction it is not enough to obtain this dynamic, to obtain the desired dynamic. So he claimed that it could be possible that adding the diffusion will result in the presence of the patterns. However, there need to be at least two different substances which diffuses with significantly different diffusion rates. So one of them diffuses really, really fast, and the second diffuses really, really slow. And then he claimed that there is a possibility that we have a constant steady state, which without the diffusion is stable, but after adding the diffusion, it becomes unstable, and it will lead to the formation of the pattern. And the idea to understand this is the following. We need to have two substances with the following dynamics. So they will interact between themselves, and one of them will play the role of an activator. I will explain in a moment what does it mean. And the second one will be inhibitor. So activator is the substance that is produced, and it stimulates themselves to even bigger production. So it means that more activator with a higher production stimulates themselves to produce. And also activator stimulates inhibitor to produce. Well, inhibitor inhibits the activator. So more activator activates the production of inhibitor, and inhibitor inhibits, so it slows down the reaction, the rate of production of activator. And this dynamics is the following. So look, first analyze the case without the diffusion. So assume we have a constant steady state with a fixed level of activator and fixed level of inhibitor. Everything is uniform, everything is constant. And now we perturb our substance, we introduce a perturbation at a certain point of the domain. For example, we increase the amount of the activator and we increase the amount of the inhibitor. And then what happens? Since at some point x, the amount of the activator is increased, it's bigger, then it stimulates inhibitor to produce. We have the increased production of an inhibitor, and since the inhibitor also slows the production of an activator, then we are again going back to our steady states. So the perturbation, it is almost immediately gone. It is almost immediately reduced, and our solution comes back to the initial state. And now take a look at the following. We consider the following dynamics, but we will also introduce the diffusion to the state with a different. And now we will assume that the activator, so the green one, is diffusing really, really slow, while the inhibitor is diffusing really, really fast. And now what happens? We take this again, our constant steady state, and we introduce the perturbation of the green, of an activator. So we have an increased amount of an activator at some point of the domain. It stimulates the inhibitor to be produced. Inhibitor is also produced. But now, inhibitor will not force activator to go back to the initial steady state. Because activator, the inhibitor, is diffusing really, really fast. Which means he will spread out along the domain really, really fast. Which means that at a certain point of x, where the amount of an activator was increased, now the value of the inhibitor is too low to force the activator to go back to the initial steady state, and it will grow even more. So therefore, now our solution will not go back to the constant steady state, but at this point x, the solution will go even higher, because the inhibitor is not able to inhibit the production of the green substance. And this perturbation will now spread along the whole domain, because here now we have the increased amount of the inhibitor because of the very, very high diffusion, which spreads along the domain, which will now here reduce the amount of the activator because the inhibitor is high, which will force the activator to go down. And since now here the activator here is high, which means that in the neighborhood, the amount of the inhibitor is too low to force the activator to go back to the initial steady state, which will also mean that the activator now will go up to some point. And now we see what happens. From the initial perturbation of the constant steady state, we obtain some non-constant steady state, like here this is the sine and cosine function, which spread it along the whole domain. And the genius of Turing was that we could stabilize a constant steady state just by introducing the diffusion. So diffusion was supposed something to introduce the homogenization, to increase the uniformity, to force the solution to be uniform along the whole domain. But now, since the diffusion are different, slow and fast, they introduce additional dynamics, which from the constant steady state produce a something like this. And now let us analyze this phenomenon mathematically. And the analysis will be the following. We consider the system of Russian diffusion. So now we have two substances, U1 and U2. Here we have the time derivatives, which explains that we have the derivative. Then we have the diffusion with two different rates, the diffusion rate U1 and the diffusion rate U2. And also some nonlinearities F1 and F2, which will describe the dynamics between the substances, between the function U1 and U2 and the function U1 and U2. So we need to impose the initial distributions and some boundary conditions which will be normal. And notice what happens. We'll again linearize it and study the linear system. So we would like to study the linear system of this of those equations. Where we have the linearization matrix denoted here by A, B, C, and D. Well, those are the real numbers. And we have two diffusion variables. So basically, using this representation of the set of an eigenfunctions and eigenvalues, we can again express our solution in the term of an eigenfunction using the coefficients a and b, and say that okay, again, using the property of these eigenbases, we can say that the system of equations the coefficients ak and bk satisfies the following system of equations, where we have the time derivative of this vector is equal to the same vector multiplied by some matrix ak. And the matrix ak, it is given by the following formula. And it follows immediately from substituting the solution, the equation of this form into this equation, and using the property that the Laplace operator on the eigenfunction ak is equal to the lambda k multiplied by the sum function. And see what happens next. We obtain that our solution is exactly equal to possesses explicit solution, which is given by an exponent of a matrix multiplied by some eigenvalue, And now we follow the following. And now let's take a look about the Turing study. So AK is the linearization matrix at the node, and then we obtain that we want to have that our steady state without the diffusion is stable. So what does it mean? Without the diffusion, without this D1 and D2, our matrix is just A, B, C, and D. So if the constant steady state without the diffusion is stable, it means that the eigenvalues of those matrices, all of the eigenvalues of this matrix, they need to be linear. And in the case 2 by 2, we have the very simple characterization of the sign of the eigenvalues, and we can say that all of the eigenvalues have strictly negative real parts, even only if the trace of the matrix is negative, and the determinant of this matrix is positive. Because the determinant is a multiplication of the eigenvalues, and trace is the sum of the eigenvalues. So, okay, under this condition, the solution is stable. And now we would like to see what happens when we add the diffusion. When we add the diffusion, our matrix A now becomes the following. So it is now the matrix AK. And you would like to study under which condition this solution now becomes unstable. So under which condition this matrix now AK now possesses an eigenvalues with strictly positive real part. So it means either the trace of this matrix is positive for some k, either for some k, the determinant of this matrix is negative. Because under this condition, we will have at least one eigenvalue with the positive real part. And notice the following. We can write the explicit expression for the trace here and for the determinant. However, we need to take into account that we impose some assumption for our matrix A. And first of all, we have that the trace is negative. Trace is exactly A plus B. So A plus B is negative. And now look, for the trace of the matrix AK, we have like A plus B. This quantity is negative. And then we have D1 plus lambda K plus D2 plus lambda K. But since D1 and D2, those are the diffusion coefficients, which are positive, lambda K, those are negative eigenvalues. This implies that this trace of an K of all matrices will be always negative. So we cannot obtain the stabilization just by forcing trace to be positive. So the only way to make it unstable is to introduce the determinant. And the expression for the determinant is a bit because the determinant of matrix A is assumed to be positive. So A times D minus B times D, it is positive. Which means that this quantity, AD minus BC, this is positive. This quantity, D1 multiplied by D2 multiplied by lambda K to the power of, it is also positive because we have only positive expressions. So the only way to make it for negative is to use this one. And how do we do it? Look, what do we know? We know that A plus B needs to be negative. Okay? So here we have like A plus B, but it's multiplied by different diffusion coefficients. Multiplied by V1 and multiplied it by V2. So in order to make the determinant negative, we need to somehow force this term to be negative, very large but negative. Lambda A is negative. Okay, this is what we like. But then we need to multiply this lambda A by a very, very large positive number. And how do we do that? So since B1 and B2 are positive, but the sum of A plus D is negative, we need to play some of those coefficients. Because now, if both the numbers A and B, they are negative, we cannot proceed. Because then this expression will be negative, multiplied by negative, it will give us the positive number, and the determinant will be positive. So in order to make it negative, one of those numbers, A or B, needs to be positive, and the other one needs to be negative to enforce that the sum is. So one of those numbers, for example, A, is positive. Then we choose the diffusion coefficient such that this term will be very, very, very small. So the one will be very, very, very small. And the two will be very, very, very large. So that the sign of this quantity will be governed by A multiplied by B. And under this expression, this quantity will be negative. And for some K, the determinant of this quantity will be negative. And we will obtain the instability. Instability, by introducing the diffusion, we completely significantly differentiate. And in order to sum up this reasoning, I would like to show you some numerical examples. What patterns can we obtain using a very simple system of reaction diffusion? So basically, this model is called the Brussel's model. This is like the exemplary model to explain the process of reaction of Turing instability in reaction diffusion system, where we have some interactions between the functions U and V. They have some biological motivation of any not explained. And we also have here the diffusions of the first equation, so like the Laplace one, and of the second equation, Laplace two. We complete with different intensities. And see what happens. Let's go back to our cat. The response of our cat on the back of our cat, and to the stripes on the tail of it. And you would like to see why does it happen that the pattern on the back is different than the pattern on the back. So we take the Brussel's model and we run some simulations. We take the constant steady state, here it is equal to 3, activated is equal to 3, inhibited is equal to 3, and we introduce the very small perturbation here in the component. The diffusion rates are chosen so the inhibitor diffuses really, really fast, and the activator diffuses really, really slow. And we can see this as the time passes. Our perturbation is not down, we don't convert to the constant steady state, but it spreads across the whole domain until we obtain a very nice diversified pattern, which corresponds to the spots on the head. But if we do exactly the same simulation on a different domain, which will now be long but very, very narrow, we will obtain that instead of the spots or stripes, now instead of spots, now we have stripes. So exactly the same mechanism, exactly the same activation, exactly the same question. The only thing that changed was the shape of the domain. So, and the only thing that changed was the shape of the domain, and therefore we obtain completely different paths. And so here, choosing different diffusion rates, different coefficients, and different model parameters, we can obtain very diversified pattern, which will correspond almost one-to-one to all of the patterns I showed at the beginning of the presentation. Like in the kind of the cookie fish, the choice of the different parameters, choice of the different shape of the domain, will lead to the emergence of the very diversity. And to sum up, I would like to conclude one of the observations that was done by Amanda, which was that very often, in the case of the class, the patterns emerges as the cats grow up. So basically, a lot of students, when they are young, they have no patterns, but as they grow up, the pattern emerges on their skin. And this is exactly the case of the check of the domain. Because if they are small, then the domain is not large enough to make so the domain is not small, not large enough to satisfy the condition of the Turing instability. So in the case of the small domain, which corresponds to the large degree rates, it means that the solution, the solution here it is stable, but only as the cat grows up. If the domain becomes larger and the diffusion rates changes respectively, we satisfy the condition for the Turing instability and the pattern on the cat's skin. Thank you for your attention.
Very much for this wonderful interaction with disability and your domain of research. Are there any questions?
Okay, so I'd like to ask you, like in the beginning, you showed us a very general form of a reaction diffusion model.
Precisely.
That you had the function f. And like, for example, in the case of the Bruce-Alter model, there were like, it had some squares and it had a linear part. So
Well,
how do you figure this out? Like from does it come from some like intuition about the chemistry of these elements, or is it more akin to seeing like what works and doesn't?
Honestly, I would love to know. Because every time you came with a new model, which produces nice models, and which corresponds to some theoretical application, you get the publication in a very good way. So figuring out a new way how to construct a model is a great discipline. Because this is what they are doing in Python. So basically, they are talking to developers, they are talking to coders, they are talking to analysts, and they try to figure out how, based on the observation, based on the reaction between the substances, between the dynamics of the dynamics, how to model it using these very simple terms like the squares, like the multiplications, sometimes there are fractions, sometimes there are more diversified functions. But constructing those models, it is always very, very hard work and requires a lot of effort.
Just a very simple question. The question is up. What is the Laplacian?
Oh yes, good point. Here is missing. Yeah, sure, this is a missing. Of course, there would be a Laplacian here, and here would be the division rates. Thank you for okay now.
Are there any other questions? Comments?
One more question. So you also the case that some of the process of natural selection play a role here. Explanation from the point of view of chemistry is one thing, but also maybe some patterns are not well adapted to survival.
Yeah, sure. Yeah, sure.
Okay, so I was thinking about this cat book, which we
Yeah, sure, of course.
Oh, okay. Yes, we explained what happens on the body and on the tail. But on the tail, I can see that those stripes become blacker up to the end. In our simulation, this inhibitor was like uniformly distributed.
Yes,
It's the same intensity, I don't know how to call it. So can you explain why this cat has this blacker stripes to the
Of course, because here we need to take into account that the tail is not separated. Because here in this simulation, well, this is like a ideal case because no one wants to separate the tail from the head. But But it is like the model, right? We just analyze the names of those two substances on only on a tail, without taking into account that the tail is connected to the body. But if you would do the simulation when the tail is connected to the body, you would have exactly the same where the pattern is strongly changing as it becomes stripes at the end of the tail.
Are the boundary conditions at the tip of the tail a little different?
Yes, sure. So for example, yeah, so this is exactly what I want here. So those two pictures which show the two different cases, the first one are the normal boundary conditions. But if you think for a while, of course, applying normal boundary condition on a tail doesn't make any sense because it's not like it's not like the domain, it's not like the square domain with the normal boundary conditions, but this is like the torus. This is maybe not the torus, but this is like the cube. So this is like the periodic boundary condition. And this is exactly what we will obtain here on the second case, when the stripes are even more visible. But very good question. Yeah, of course.
So what happens in the case when our domain is unbounded, but it shrinks in one direction in such a way that the measure of it is ultimately finite?
Well, that's a hard question. Because when domain is unbounded, then we have a problem. Where is it? With the spectral theorem.
No. If the measure is finite, still you have this decomposition.
Really? It is not. Okay.
The measure is
Okay. So I didn't know that. I thought that if we have the unbounded domain, then we always have the continuous spectrum.
usually when the measure is infinite, yes.
Okay. So I honestly I don't know because I didn't run the certain experiment and I didn't work in this case. But this is a very good idea to study this case. So we'll discuss it in a moment.
Are there any other questions? Maybe I ask two questions, one about the past and one about the future.
Sure.
One about the past concerns the prize, the international prize, like where was organized by Polish Mathematical Society. And just describe very briefly your opinion, the one result, and then in the future, what are the open questions or reactions?
Sure. Well, so maybe I'll start with the future because this is what bothers me, Grzegorz Kark, and all people in the department. Was like, okay, that I was a bit cheating here because when I consider this reaction diffusion system, I only showed the stabilization of the constant states. I didn't show that the patterns really exist. I showed that if I have a constant steady state, it will not be stable and it will diverge. So it will become unstable. But we don't know, of course, it's not known if from this instability something comes out. So it will lead the emergence of new patterns. And in fact, this is an open question for like 8 years. So when in 50s, Turing introduced this concept of Turing instability, a lot of people tried massive or extreme amount of different techniques just to prove the existence of non-constant stationary solutions. In some cases, it is possible using geometric singular perturbation theory. Sometimes it can be achieved using variational approach and so on. But this is extremely complicated. So now we try to work. We try to figure out how, in this case, provide as general procedure as possible to construct non-constant stationary solutions. So, well, that would be a bridge solve this problem because it's like open question and a lot of people bother with that. But we will focus maybe in some in some special case and other special aspects. Yeah, of course. And about the past, so my main result was concerning when the first diffusion here, D1. How this works? Yeah, it works. When the first diffusion here, D1 on the battery was equal to 0, and we showed almost complete procedure how to construct those stationary solutions of the diffusion, how to analyze the stability, and we proved that in the case without the diffusion, with the first equation, the system is much easier to study and a lot of things can be shown. Yeah, sure. Thank you very much.
Okay, thank you. Are there any other questions? No comments? It's so clear exposition, so you know everything now, almost everything. Thank you very much again.